Alright, welcome back Physics 30. Today's lesson, like last time, it involved two different lessons in one lecture video. The reason that I'm doing this again is because if you think about it, we learn about atomic models. So we need to go through Bohr's energy level situation, which is lesson number 8. But we need to understand how EMR spectrum work because here's the thing. If you think about Rutherford's law, Rutherford's planetary model suggests that electrons have to go around the nucleus. But the thing is, whenever that happens, electrons go around the nucleus, it is circular motion, so you are undergoing centripetal acceleration. Because of that acceleration, you should technically emit EMR. But how can that EMR can be interpreted for us? So lesson number 7 is a little bit of a pre-lesson for lesson number 8. How can spectrum come out from atom? There are 3 different ways. If you want to memorize, feel free for memorizing, but gonna explain as easiest as I can, hopefully. First thing first, we know this most of the time, continuous spectra. If you think about any type of industry, like you're doing mining situation and collecting a hot molten iron, something like that, or if you watch like Lord of the Ring or any type of Middle Age era film where a blacksmith make weapons, how can we know that spectras occur with that? It's because if you hit any type of matter, solid, liquid, and any type of dense gas, they emit EMR. But in fact, they emit every single EMR that it can possibly emit. Most of the time, it's visible spectrum, IR, those kind of things. So, continuous spectrum basically means it's a band of spectrum. Rainbow. Some people say, Mr. Kim, I do remember having or seeing orange color from the metal from that movie, like Lord of the Ring, orcs making weapon, those kind of thing. It is correct, but you need to understand this. Our eyes can only identify very, very tiny portion of electromagnetic radiation. In fact, it's a rainbow. We cannot see anything below, we cannot see anything that above. Red all the way to violet. So, here's what happened. Imagine light bulb. Light bulb is a wonderful example. Inside there, you have a tungsten. That's a metal that have a highest melting point, if I recall. That's one of the reasons why Edison used tungsten light bulb. If those are heated up, it actually show like yellowish light and so on. So in order to identify a little bit further, we use prism. If you guys remember in Unit C Part 1, there are 2 different objects that make a diffraction and bending of the light. Prism, refract, and I know it's not in here, but diffraction, grating, like the word suggests, diffract light. They separate light. But there are one thing that you need to memorize, if you will. Prism, if you go through that, it go rainbow color from top to bottom, which is red as a star, violet as the last, something like that. But on the other hand, if it's diffraction, it's go other way around. Violet on the top, red at the bottom. So it's kind of go down to up situation. I believe in my lesson video of refraction and those kind of thing, or I believe it was going along with ray diagram, but as you may notice, I asked you to read it, but I didn't go through just because it's just that relationship. So in fact, actually it could have been Young's double slit lesson, but in any case, you can look through that. So number 1, hot object was prepared. And number 2, he went through prism or diffraction, grating, something like that. Grating. If it's go through the prism, you will have a continuous band of light. red to violet. If it's diffraction grating, which is also can be number 2, then you will have violet on the top, red at the bottom, something like that. Don't freak out when you see any of those in diploma, just for the heads up. But in any case, spectrum was fully shown because they have all frequency from the source. There was no gap. So EMR happened because of the collision between atoms. When it comes to hot, if you guys think about it, high temp means high kinetic energy. That means high number of collisions. That is basically kinetic molecular theory, the one that you learn in chemistry 20 for ideal gas and collision. But in any case, that's one thing that you need to have it in your mind. Now, emission spectrum. Let's think about it. Emission spectra talk about low pressure gases exposed to high voltage. So, few things that you need to understand. The condition, low pressure gas, but they exposed to high voltage. So, if that happens, you're going to experience some kind of excitement. And low pressure is actually one of the most important part. Now, if there's a high voltage happening, I want you to think about high excitation. Then, if something is excited, you will know that I'm talking about like time situation. As time go, you're gonna have less excited, which is relaxed situation. The thing about any type of atomic spectra, electrons and subatomic particle, but electron most of the time. Electrons is the reason why we have a color given, like in neon signs, something like that. But one thing that you need to understand is, whenever you have highly excited situation and then it goes to relaxing state, what electron does is electrons emits light. But they emit certain light. So if a certain voltage was set up, it may show green color, red color, yellow color, those kind of different color, as long as you have low pressure in it. The reason being is, if I have low pressure, that means there's no excitation. If it's high pressure, there can be excitation because they're gas. They will collide a lot. So that's why I start from unexcited situation, but you suddenly excited and make it relaxed. Then what's going to happen is you only see certain band of a color. In this case, I have red, green, blue, and violet. Then what happened to some other color like yellow, or you have indigo? These guys just are not the light that is coming out because we basically don't have any energy differences that are undergoing by electron to emit that light, which will be explained to you way more in lesson number 8, because that's Bohr situation. So at this point, please understand that emitting a certain light is happening because of excited atom, and during their relaxation, that's what they happen. And each atom's excited differently, so that's why you have unique emission spectrum. That's second part. We call this, like the word suggests, emission spectra. Number 3, absorption spectra. This is a situation where you have entire color spectrum with certain dark bands. That's what I want to point it out here. So that means, let's think about what we have first. You have a hot object as a start. That's number 1. So you may notice that at this point, you have all EMR. You can think in it that way. Not literally everything. Like we're not going to have a gamma radiation from it, but you got the idea. Like visible spectrum, IR, those kind of thing. Now, I kind of generally said all EMR. However, this is important. You have unexcited hydrogen gas. That means they can absorb energy. Energy from where? Energy from EMR. Then what's going to happen is this. Because it's a hot object, yes, hot objects should show all band. But because some are absorbing the energy, it can be hydrogen gas or something like that in this situation, you will see some dark band at this location. And this phenomena is known as absorption spectra. Now you may notice, and I did it on purpose, can you see I put excited hydrogen, unexcited hydrogen? I want you to look at the result. You may see that there is a nothing but color band for red, green, blue, violet. Can you see and compare the result for the absorption spectra? You may notice that at this point, red, green, blue, violet also. So I like to say unique pattern for each atom is what I want to point it out. It's just different method of showing the band. So some are excited and it show you that bright band, or some are absorbed, so that's why they show black band, but the location doesn't change. And that's what is important. Let's do one example. And I know it's a homework part, but you will do it most of the time, but let's see. This question is quite DQ-like, diploma question-like, but you may notice it's one of the easiest one that you will see. And honestly, people use it all the time in astrophysics, because every planet have gas, and those planets have excited gas or unexcited gas, and depends on those hot or cool kind of planet, you will know that, oh, that's an absorption going on, or there's emission going on, and what kind of gas is in there. They use bands. So let's do this example. So an information is given. Emission spectra have 4 common elements, and they have hydrogen band given, sodium band, helium band, and mercury band. And basically we are trying to identify, imagine these are different sample, unknown sample, or any from different planet that you just discovered from NASA, something like that. Let's do a B in here as an example. You will do the other parts. But I have one band that is below 650. If I look at that band, I cannot choose sodium as that band explanation because there's nothing, or I don't have any for the mercury. So it must be hydrogen or helium in order to have this band. But I want you to look at my other clue that is given. So what I mean by that is, do I have any band before 550 nanometer? If I look at it, yes, there's one, but it's kind of hard to see because there are 2 of them. So I'm not too sure. They're existing. Hydrogen doesn't, however. Now let's go to 500 to 450. If I look at these 3, can you see that I have 2 band over here? I only have 1 band. So there is a possibility maybe it's helium, but in order to be helium, can you see I have 1, 2, 3, 4 band? Do I have those? 1, 2, Around this 450, I have nothing. If I have helium, I should have one band over here. So helium is out of the picture. Then let's find out if hydrogen is a case, because I should have one kind of closer to 500, which is this one over here. That one's also confirmed by same reason. And do I have another band right before 400 and a little bit middle-ish? And we do have it. So one of them must be a hydrogen. Then what would be the other two? This double band is a big clue. There's two that has a double band, which is sodium and mercury. But in order to be sodium, can you see sodium have nothing on the left side and right side but this double band? But if I look at it, then I shouldn't have this band over here or band over here, because sodium doesn't have it. But I have those two, which means it must come from mercury. And mercury's example, the big thing is, can you see there's one at the end? That's a big idea, that mercury must be the other element. That's what you can do. Now let's continue. This is one of the most important discovery, and because we are still using it, we just use with the quantum mechanic, but let's not go to quantum physics now. Bohr's model. Long story short, I'm going to explain to you what he said. His idea was this. Yes, it is true that electrons go around the nucleus like planet. However, what he suggests was each electron have its place. They orbit to certain level, which is known as stationary state, and when it comes to that stationary state, the electron must have exact energy to stay there. And as long as, for example, this electron at the most smallest radius over there, as long as that stays in that level, it's gonna be unexcited. It's gonna stay at that position. That's his idea. And that is basically what we found as an actual answer too. Because if you think about it, copper, if you burn copper atom, then it's gonna have green flame. If it's sodium, yellow flame. The reason that we have different flame color is because they have different energy level and electrons come back to itself. So here's the thing. He also suggests that there's, of course, different level of electron orbit. However, the lowest orbit is known as n is equal to 1, that require the least of the energy state, and those are known as ground state. That's unexcited states. So this is his quantification. Inside of the atom, you have these different energy level. And you don't need to memorize these values. Negative 13.6, negative 3.4, negative 1.5, negative 0.850, something like that. You need to understand that in each level, you have a certain electron level, and in order to make this electron over here to go to the other level, you have to have exact different energy to get to this level. If it's something more or less, it's actually choose to come back. This is what we like to call as ionization, because here's the thing. It's kind of like work function too, if you think about it. If I have more energy and then go up, 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 up like that, so in this case 0 to negative 13.6, so if I have any energy that is bigger than a gap of 13.6 electrovolt, then what's gonna happen? It's gonna go out. That is like work function. And what does that make the whole atom? That means if this was copper atom, Cu solid, then it's gonna be Cu positive. And that's where ionization happens. Ionization is basically introducing electron or removing an electron. So in this case, the minimum energy to remove an electron from an atom is known as ionization energy. And this is basically, if I recall, hydrogen ion as a base, and then it turned out 13.6 electrovolt is enough to make one goes to another, something like that. It is significant to understand the relationship between your electron level and how much it required to go one level to another. Like what I said, if it's not enough, then it's going to come back. So you have to be exact energy it is required. If I go lower level to upper level, we kind of say it's excited. If it's on the other hand, go from upper level to down level, it is absorbing because it's relaxed. There you go. I almost did a very bad mistake. If I excite, you have to absorb an energy to get excited. It's like you have cold water to boil the water. You need to absorb heat energy. In this case, EMR energy. If I have higher level to lower level, that's relaxing and that emit light. These are the relationship that you need to understand theoretically. Now let's do one example. An electron orbit bores hydrogen atom with the radius of 4.76 10 to the power of negative 10 meter. Determine the orbital speed. Well, we know that. I'm going to use this picture. I have proton in the center. It's actually proton and neutron, but we're not talking about neutron in here because it's not charged. Proton in here, electron go around. So there is a centripetal force. So in this case, my net force is just electric force. It's an attraction between those two. So I can say mv squared over r is equal to q1 q2 r squared. Q1 will be my proton, Q2 will be my electron. Fortunately, these two share the same thing. In terms of quantity, 1.60 10 to the power of negative 19 C. So we can find orbital speed. First of all, can you see R and R? Multiply 1 R to each side, so R will be disappear. V is equal to KQ1 Q2 over Rm, then square root them. And we're talking about electron over here, so mass should be, well, mass of electron. Let's punch the number in. If I round it up, it has 7.29 10 to the power of 1, 2, 3, 4, 5 meter per second. That's what we have for the speed of electron that orbit around the hydrogen atom. Let's do some other. Alright, when I look at this, there's energy transition. Like I mentioned, first thing first, EMR can be emitted or absorbed. To have emitting situation, you have to go from upper level to lower level because you relax. In order to get excited to relax, you need to use up the energy. Absorb, lower to higher, like cold water boiling to hot water, you need to absorb. So here's the thing. Photon to be emitted, you have to know the upper energy level to lower energy level. And it should be that specific value. On the other hand, if it's absorbing situation, photon absorb, exact same differences, except I can just added up the number, something like that. It's opposite of subtraction. But long story short, we are gonna look at it as an absolute value because the gap is what is important. So let's do the situation. The total energy of orbiting electron is negative 7.15 electrovolt. If it's then emits that much of photon, determine the total energy after emission. First thing first, we know that electron, in order to emit it, you're going upper level to lower level. Have that in your mind first. Now, the total energy that should be involved throughout this process is, well, it's emitting EMR, right? So HF over, in this case, HC over lambda, which is, and I'm going to use probably the electrovolt that we have for H value, which, oh, I forgot. I always go with 6.631. 4.14 10 to the power of negative 15. There you go. 4.14 10 to the power of negative 15 times by 3 10 to the power of 8 divided by 260 10 to the power of negative 9 gives me about 4.7769 electrovolt. And if you think about it, that is how much of energy that you need to lose. So remember, if this is negative, this is way more negative value when you go to lower level. So here's what I need to do. Negative 7.15 electrovolt minus 4.78 will give me my after the emission. So negative 7.15 minus 4.78 should give me negative 11.93 volt, rounded up to 3 significant value, like that. Similar thing, sorry folks, in my workbook answer I have negative 2.37. The thing is, ignore that answer. You should have more negative value. Again, my rookie part. Let's do more diploma-like question at one point. So you are trying to find a electron that is initially unexcited, and you're trying to find out what happened to this atom if you receive these following energy. So electrons originally here. It says receive, so that means absorb. So you're gonna go up from lower level. So let's talk about this. Negative 17.0 electrovolt plus 8.00 electrovolt. If I add them up, then you're gonna be located at negative 9. That means, can you see that I have negative 9.0 for the second level? It's the exact same value. So you can say it will be located at n is equal to 2. That's what it is. If it's, however, 10, negative 7. Do we have negative 7? No, negative 7 is in fact somewhere in between. Then nothing happened. It has to be no excitation. Exact same reason. C, 20. It's positive 3.00. Do we have any positive? No, in fact it's 0 and positive 3 is somewhere over there. That means electron will go all the way up and it's go out. So I like to say at this point it is whatever infinity level. So that's a fancy way of saying beyond 17.0 eV. So energy is beyond that. So the atom is ionized. It'll be like whatever positive situation. It's a simple adding and subtraction, but it does talk about a lot of exciting absorbing in this situation. To what level you need to identify. Now our last portion of it. Like I said, today's lesson will be long. Bohr's explanation about excitation of hydrogen spectra. Well, here's the thing. So, if you guys remember, low pressure hydrogen gas, and there's from that process we apply high voltage, so light was emitted, and then these are basically the band that we have. It's not continuous, it's an excited one. So Bohr was thinking, and this is his experiment, right? Why does excited low pressure hydrogen gas emit only certain frequency? And this is the reason why he started thinking. It's because a certain energy level emits certain light. So he first of all discovered these lambda. And from this lambda, he did, H is equal to hc over lambda calculation and try to connect with delta E, upper versus lower. And from that, he went to the conclusion. Anything that involved with, let's start from the bottom, UV light must have highest energy. So that means it can go from the 1, 2, 3, 4, 5, all the way to 5 level, 2 entirely down, 4 level entirely down, 3, 2, 1. Oh, sorry, it's actually 1, 2. That's 1, 2, 3, 4, 5, 6. Sorry, 6 to 1, 5 to 1, 4 to 1, 3 to 1, 2 to 1. Bohr was able to show that energy level and connect it to the diagram. That's how much it's basically releasing the energy for the UV. On the other hand, for visible spectrum, now let me go to this picture over here. If it's red, it was 3 to 2. That was amount of energy. If it was green, it was 4 to 2. Because green energy have higher energy. Red has a least of the frequency, so no wonder least of an energy. But violet have highest energy because highest frequency, right? Like that. So green was 4 to 2, blue was 5 to 2, violet was 6 to 2, something like that. UV has the most, so that's why everything was done in that way. On the other hand, some of them that show, Mr. Kim, what about the one that have 6 to 2? It doesn't go to the ground level. Or anything that goes to, actually, sorry, 6 to 2 was violet. Oh, this is the one. 1, 2, sorry, that was a 3. Yeah, it is right. 6 to 3, I cannot count. 3, 4, 5, 4, 6, and 5. There you go. What about 6 to 3 situation where it's not a visible? 6 to 4, 6 to 5. What about those energy? Well, those are turn out to be IR because they're having such a minimum energy, and then that was shown as a heat energy rather. IR is a heat energy. So during that spectra, he was able to explain why a gas excite and absorb the same frequency of EMR that is emit. He did the same experiment with absorption spectrum. And Bohr knew that A hydrogen atom drop from certain level to another level. If it's upper to lower, it basically emits light with a certain energy level all the time, which is shown as 2.56 electron-volt in this case. And in order to absorb 2 to 4, it involves same quantity, 2.56. The only photon capable of providing the exact energy was the reason why electron can be excited or relaxed. So from the Bohr's model, it could explain the emission and absorption of spectra for a hydrogen. And it does explain at one point that, you know what, maybe at the stable level, we do not lose or gain energy, because the only time that you can do is what we just look at it, absorb energy or emit energy. But there are still quite flaws in here. Number one was the spectra for more complex atom, more than one electron. Hydrogen have one electron, so it was easy to calculate. But what about gold, heavy metal? Or still, why only certain orbital do we have to go? Why not in between? Or third, why the orbiting electron did not emit EMR as predicted by Maxwell? This ultimate answer that gave Rutherford model a hard time was not answered. And why some spectral lines were brighter than others? Why not same intensity? Those were hard to explain. And that one is basically the introduction of quantum physics. And we're going to put a pause button. I want you to work on the homework section for Bohr's model and spectrum one. Bohr's model related question, you can find it on page 67 all the way to page 69. Know the fact that I know there's a lot of questions, but I kind of want you to try them all. It is one of the most important DQ questions that you will see. So that's what I want to point it out.